Okay, so welcome to the first session on the Measuring the Quality of MCMC Output workshop. So this event was organised by Pierre and I on behalf of the BayesComp or Bayesian Computation section of the International Society for Bayesian Analysis. And the free registration, which covers the GatherTown costs, comes from the QUT Centre for Data Science. So there are a few aims for this workshop. Firstly, sharing exciting research on MCMC and measuring sample quality and looking at diagnostics in MCMC. So we want to bring together people working on methods, theory, and practitioners as well of MCMC. We also want to look at networking. So for some ECRs and PhD students, they might not have had the chance to attend many or any in-person events. So we're giving an online event before in-person events get started again. So in keeping with that, we ask that everybody please put their videos on. If you've got a webcam, it'd be great to see everyone's faces so we can all get to know each other. The other aim is to create resources. So we've got this website here, which we've sent links to before, and this has all of the material, links to all the videos you've created and slides and posters and things like that. So hopefully that will be useful going into the future as well. So to give a bit of background on why this is happening and how it came to be, as I said, Pierre and I are the organisers. I'm a lecturer at QUT and Pierre is a professor at ESSEC Business School in France. And we're both in the BayesComp committee for the BayesComp section of ISBA. So I'm the secretary, Pierre is the program chair. And we're the section that organises the biennial BayesComp meetings. So the last one of those was in January 2020 in Gainesville, Florida. So some of you would have been there. The next one's not going to be until 2023 though, because of COVID. So hopefully that'll be a great conference, but we didn't want to wait until then. So we thought we'd organise some online events in the meantime. And this is the first in the series. So if you're interested in Bayesian computation, you might like to join the section. So there's a couple of links here that you can do that through. And basically, we provide money to help students attend conferences. We fund poster prizes and presentation prizes, and we also hold events like this. So this session has been run a little bit differently to normal conferences. Essentially, you know that most of the content, the longer pre-recorded talks are available online. And we're trying to focus on live interactions during the actual session. So essentially, each session is going to involve some brief introductory words from us to start with the introductory words being a bit shorter in the next couple of sessions. Then we're going to have some short 5-minute talks from some of you participants, basically advertising typically some longer posters or pre-recorded talks. Then a group discussion, which is similar to a panel discussion, but open to everyone. And then a longer poster session on GatherTown. So you can go around and look at posters. Also, slides are going to be there for people who've got talks. Okay, so the reason it's a bit different, there's several reasons for it. Firstly, we wanted to give lots of opportunity for live interaction and to foster good networks. Also, there are 13 different time zones involved in this. So it kind of makes sense that you're not going to want to watch all of the talks at once. So it's a bit of an experiment, but we hope you'll enjoy it. We're going to send out a survey at the end of the last session. So please let us know what you think for future events. Okay, so now let's get on to the actual MCMC. So I'm going to set some notation and define some terminology. We're interested in some target probability distribution pi, which might be on some space, for example, the Euclidean space, discrete space, the space of trees, and so on. We might want to approximate pi itself, or maybe approximate some expectations with respect to pi. And MCMC helps us to do that. So in MCMC, we have, we want to get a pi invariant MCMC chain. So we have a pi invariant Markov kernel P, and we have an initial distribution pi naught. So we get our initial sample x naught from that distribution, or maybe we just have a fixed value. And then we move along using this pi invariant Markov kernel. So setting some notation, the distribution of xt is pi t. So we know that if we were to take t to infinity, then we get consistent approximations, but of course taking t to infinity isn't feasible. And if we were to start from actually drawing from pi, then we get unbiased estimates, but also that's not feasible. So in practice, we have some starting point, which isn't from our target distribution, and we have a finite number of steps. So that makes it difficult to assess our sample quality. It makes it important, to assess our sample quality. And there's a couple of things that complicate it. So relative or compared to basic Monte Carlo, when we can draw IID samples from pi, the two of the main complications are that pi t isn't exactly pi. And also we have autocorrelation in our chain. So xt is not independent of xs for any t and s. Okay, so one of the things people focus on typically when they're looking at MCMC and diagnosing their chain is they look at, have I achieved convergence? And that can mean different things to different people. But a couple of the things people typically refer to are, has pi t converged to pi, or has some measure of distance between the two, such as total variation distance, gone to 0. We also might be interested in, are the estimated expectations going to their true values? And we know that as t goes to infinity, the sample estimates have a normal distribution centered on the true value and with some variance that depends on the kernel and on the function of interest. So in practice, we want to think about how do we actually choose this burn-in period, so the initial set of samples that we remove, and how do we pick t? We also might like to think about how can we estimate this variance, because that would be useful in deciding when to stop and also in constructing things like confidence intervals. So it also might be helpful if we could actually talk about the convergence more concretely. So it can formally be shown for some Markov chains that we have geometric ergodicity, which is this thing here, or for other Markov chains, we might have polynomial ergodicity. So this might be useful, except it's difficult to work out the constants. And so that makes it less practically useful, except for in certain settings when we can estimate the constants. Another thing that makes this challenging is that estimating the distance between pi t and pi is hard, because we can't actually sample from pi and we can't evaluate pi t. So often we resort to things like visual diagnostics. So we might do something like a trace plot, and we might look at each of the different components, so the target log density, and maybe some other functions of interest. And then maybe we'll have multiple different independent chains starting from different points and seeing if they appear to converge to the same thing. We can also look at coupling to assess the non-asymptotic bias. And I think this is a good point to pass over to Pierre, who has a lot more knowledge about that.
Thanks, Leah. Hi, everyone. So yeah, I'll go forward with explaining this work of Val Johnson from '96 using coupled chains for convergence diagnostics. Can you go on to the next slide, please? So the idea was to run many chains, number C of chains, that would all be generated in such a way that each of them is our MCMC chain of interest, but jointly they all coincide after a certain random time called the meeting time, denoted by tau here. And so if we can do such construction, which doesn't look like it's easy to do, but in some cases Val Johnson managed to do it, and so there are recipes to do that. Then we have this upper bound on total variation distance between pi t and pi in the form of a product of a probability that the meeting time is larger than t. So that's not going to be something we know analytically, but if we generate lots of coupled chains that meet, we'll observe the meeting times, and so we can replace this probability by an empirical estimate. And now it also involves this, this other quantity, 1 minus r to the c, where r would be a rejection rate from the initial distribution pi 0 to pi. So the idea would be that if we have C chains, there's a little chance that we can consider one of those C chains to be actually distributed from pi. For example, because in the rejection sampling algorithm proposing from pi 0, there's a little chance that we would accept a draw from pi. And so unfortunately that number might not be very easy to estimate in practice, especially in the MCMC setting where we wouldn't think of rejection sampling as a viable option. Next slide, please. I'm going to go on with some description of other classical topics in MCMC diagnostics, in part because some of the contributions that you proposed in the poster slides and videos are basically extensions, improvements over those classical topics. So there's a question of asymptotic variance estimation, the asymptotic variance being the variance in the central limit theorem that Leah presented. So there's a lot of literature on that, variance estimation, not only in MCMC, in many other settings. It's important to compute the so-called long-run variance of a stochastic, of an ergodic average. But it's been particularly looked at in the MCMC literature as well. And that in turn is central in defining notions such as the effective sample size associated with different components of a markup chain, and stopping rules, which would be ways of automating the choice of iterations by, in a sense, running until the confidence interval associated with our estimates are considered small enough. Next slide, please. So the asymptotic variance is not easy to estimate itself. I mean, this would be one definition of it, the limit of this rescaled variance. For a certain test function h of interest, that could be the identity or a function mapping the state of the chain to one of its components. And the reason it's hard to estimate from a single chain or from a few chains is because it involves many covariances and that are hard to estimate from few trajectories. Lots of terms to estimate basically from the sample. Even assuming stationarity, which would be assuming that we know a good choice of burn-in or warm-up, there's a lot of terms to estimate. And so, for example, in the effective sample size that is typically reported along with MCMC outputs, this type of calculation arises as the definition of the effective sample size is the number of iterations divided by this quantity at the bottom here, involving all those correlations, meaning that this is the sample that would yield a variance equivalent to IID samples of a number given by this quantity. Next slide, please. So there's been lots of efforts and discussions along the topic of MCMC convergence. There's a classical long-run, short-run debate. For example, Charles Geyer has been writing that if you can't get a good answer with one long run, then you can't get a good answer with many short runs either. In some cases, people in fact run chains for apparently trillions of iterations. I found a trillion in a paper using MCMC in the context of gerrymandering, actual trillions. Right? So the problem being we don't know exactly how many iterations to run, but we don't even know the order of magnitude. It could be from a few dozens to trillions. And then the context also changes because parallel computing obviously makes a big difference nowadays. We can run, in fact, many parallel chains, and that is useful to compute certain diagnostics. So, for example, the Rhat diagnostic, classical Gell-Mann-Rubin diagnostics from his 1992 paper. Next slide, please. So this is a definition of this classical Rhat diagnostic. I know that some of you propose improvements. So we're all excited to hear about that. But this is the classical version from 1992. It's basically a ratio of. There's an issue here. There should be W plus B over T, where B over T is a between chain variance. So you have C chains. Each of them run for T steps. You compute an estimate of interest. You compute its between chain variance, its within chain variance, and the top part of the fraction above is an estimate. It's called a pooled variance estimate of the target variance, the variance of X under pi. The denominator W is itself a consistent estimate. And so the ratio should go to 1. But on top of that, the numerator is overestimating the actual target variance if we assume that we have started the chains sort of in a spread out way, so that the between chain variance will be overestimating the target variance initially. And so then having this quantity that goes to 1 from above, we can decide to stop to be happy with the calculations if the Rhat goes below a certain threshold, for example, 1.1. And so this is the basic idea of the Rhat diagnostic, and there is a lot of interesting variants of it. Next slide, please. So again, like it's a hard problem. I think it's important to appreciate that, and that there has been decades of research on the topic. It's a difficult problem, again, because there's no really any default number that would work well across different applications. And MCMC has a lot of applications. We'll come back to that in a second. So in a sense, we would want to not think about iterations at all, right? So for example, we would like to specify a tolerance, like in optimization, or a certain time budget, let the algorithm run until the desired precision is achieved. But there are stopping rules in the literature on diagnostics of convergence, but most of the time, people would specify numbers of iterations as of still today. And this is not convenient in practice. So some quotes on the difficulty of convergence, for example, from Brooks and Roberts, 98. As with all statistical procedures, any convergence diagnostic technique cannot be guaranteed to successfully diagnose convergence. And this has been formalized further. For example, this Pat Nagar, Bogdanov, and Mussel paper sort of explains that you can frame the problem of diagnosing convergence from the samples generated by the algorithm as a problem that is in a certain class of complexity that might make us feel a bit pessimistic. Next slide, please. So there's been also attempts at trying to completely avoid the problem. So one of the perhaps most striking one would be regeneration. So the classical paper is Mikland, Tierney, and Yu, 95. And regeneration consists of identifying in a trajectory of a chain, as in the graph, times, like here shown in vertical bars, such that we can take the segments of the chain between the times and consider those segments to be IID from one another. So are independent from one another and IID. And in that case, we could estimate the quantities of interest slightly differently by doing an average by this ratio, the denominator being random because the length of the tours becomes here random. So this, of course, requires us to be able to identify those segments, so identify those tours. The 95 paper shows that it can be done in certain non-trivial MCMC settings. This is a technique that has received a lot of enthusiastic support, I think, initially, and then currently it's still not really mainstream. It's not, for example, implemented much in statistical software. Next slide, please. Yeah, I'll let you go on with this part.
Okay, thank you. So this is now something a little bit different, measuring sample quality in a way that can be done beyond MCMC, but is particularly useful in MCMC. So this is following the references down here. So essentially, we've got a set of samples and we've got a target distribution pi. So we can use these methods that just require that we know the gradients of the log target density for each of our samples. So the idea is that we can compute some discrepancy between the samples and the target distribution based on the samples and the target gradients. So you can kind of picture a very simplified version of this is that the gradients of the log target should have 0 expectation if the samples are actually from the distribution. So you could try and look at what the actual expectation of the gradients of the log target is and see if that's close to 0. So that's I believe it's a very basic version of that, but there are more sophisticated versions that are actually convergence determining as well. So one of the things we wanted to say is that we might want to wide range of convergence diagnostics and tools for measuring sample quality in our toolbox. Because just among the participants who've registered for this workshop, these are the range of applications that were mentioned. So MCMC is used in a wide range of applications, and you can imagine that in these different applications, there's going to be different challenges. So depending on the application, we might be more concerned about multimodality, about the fact that it's a discrete space or something else, or even computational challenges. So we might like a variety of tools for that reason. And also because we might want a variety of levels of guarantees. So you can imagine sometimes you might want just a quick and dirty check of your MCMC because you're doing it for something that's relatively unimportant, that it doesn't need to have too many checks. But then other times you might want to be a lot more confident. So you might want to use a more expensive test. So basically we suspect that there's room for a spectrum of computational methods, from cheap with few guarantees to expensive with strong guarantees. Okay, so that's it for our introductory part. You might have noticed that there's 3 sessions. The first one obviously is now, then there's one next Thursday, and then the Friday after. So this first one is on a general view of MCMC diagnostics, kind of talking about the history and the limitations is what we're going to focus on a little bit there. Then looking at new and modern specific samplers and applications and challenges that come up there. And then finally, theory and practice, bridging gaps and ways forward. Okay, so I think that's about it for now. We might move on now to the short talks. I think we might stop recording now in case people aren't comfortable with their short talk being recorded.